see. And I can do that. All right, I think that we are good to go. So I want to welcome Joe Bayley, who is joining us today from the University of Glasgow to talk about gravitational waves from neutron stars. Take it away.
Okay, thank you very much. Thank you for inviting me to stand there. Yeah, so from the University of Glasgow, we've got quite a big group of people there. It's about 60 or 70 of us working in gravitational wave research. That sort of stems from sort of experimental research and developing the detectors, and it's that data analysis side where I work. And there's quite a big focus on machine learning because that's very popular. But today I'm going to talk about neutron stars and how we search for those and try and identify them in gravitational wave data. So just a little outline. I'm going to introduce gravitational waves, what they are, why they're useful, why we're interested in them. Talk a little bit about detectors and how we actually search for these, or how we detect them, I guess. Then I'm going to talk a bit about neutron stars and what we're searching for and why they're interesting as objects to look for. And talk a little bit about how, as a collaboration, we search for these signals and techniques we've developed at University of Glasgow to search for them as well. There's a lot of challenges associated with searching for these kinds of signals, but I'll come back to that later. So initially, what are gravitational waves? So these all stem from Einstein's relativity, general relativity. Where you can sort of see space-time is this fabric, which if you put some mass in there, it curves that space-time. And there's this sort of famous quote from John Wheeler, which says, space-time tells matter how to move, and matter tells space-time how to curve. And so from this description, you can also get gravitational waves, right? So these are just ripples through that space-time. That's what we're interested in. So there's sort of a completely different way to view the universe and objects within it. We sort of use the electromagnetic things from radio, X-ray, and everything else, whereas these sort of offer an unobstructed view of the universe, because these are very weakly interacting with matter. So you can see further back in time and further in distance. Further in distance because it's not blocked by dust. So we're interested in these waves, but how do we sort of interact with matter? So they're weakly interacting with matter, and what do they do? So you can imagine sort of a ring of masses in sort of inertial frame or a circle, and as a gravitational wave passes through, so they'll be coming out or into the screen here. These masses are sort of stretched and squeezed, and so this is sort of one wavelength across these four. But these are very weak, so this is a highly exaggerated sort of view of what a gravitational wave does. We sort of measure this by what we call a strain, so that's this H value here. And that's incredibly small. So for the first binary black hole, I think this is a strain of about 10 to the minus 21. So you can imagine if the detectors have about 4 kilometers of length arms, and so you have this delta over L, where L is the length of your sort of detector, you can say. And so the change in length of that is about 10 to the 3, so about 10 to the minus 18 is the amount sort of your detector will move. These incredibly small values, which make it quite a challenge to actually detect them. So how do the detectors work? So we use interferometry to detect these signals. So this is basically you shine a laser on two arms which have the same length, the same path of the light. And the beam then comes back from the mirrors at either end and recombines. So we'll wait for this to come around. So it bounces off the mirror at either end, comes back, and the wave can interfere with the other arm back at the beam splitter in the middle. When they combine, you get some interference. And say if it was destructively interfering, when the mirrors aren't moving, when those mirrors move, you get constructive interference, and you'll see some changing in the output of the detector. That's the most basic idea of how this works. And as a gravitational wave passes, these two mirrors should move, and you should see some change in the output of the detector. So that's the basic idea of how they work. Obviously, the detectors are much more complicated than that. You can't just put mirrors at the end of two arms. There is a lot that goes into it. So I'm not going to explain all the parts of this diagram. It's not really necessary, but it's more just to show there's a lot of complications with these. You have to suspend your mirrors from like small silicon fibers at the end of each of your arms to try and sort of isolate them from any noise. And there is a lot of different noise sources. So this plot up here is sort of a diagram showing a few of those. And this includes sort of noise of the coating of your mirror. So you have sort of thermal motion of that. And the same with the suspension pipes as well. And there's noise from all the ground around you, so seismic noise. You can always see things like trains going past or clouds moving overhead. You can detect in there. You have to try and isolate your detector as much as you can from these different sources.
Clouds moving overhead.
Yeah, so sometimes if you have a cloud moving overhead, you can see it. Well, sometimes in the other channels, it's obviously taking most of that out. It's low frequency.
So that's just a continuous source of noise that they know how to take out.
No, so the noise, that noise is sort of dealt with because you have lots of other instruments around there which can sort of actively remove that. So that is one thing you can see in the data as well.
Is it the what is that the cloud does it? Is it
The
the
mass.
gravitational?
Yeah, the mass of it. So you can call that, there's things like Newtonian noise as well, which is that static consciousness thing, which is just like a tilt in the ground.
Right.
So one thing I see quite a lot is wind. So certainly at the Hanford detector, when wind blows past, it blows on the side of the building to the tube and sort of lifts it up.
That makes more sense.
That's a bit stronger. The clouds are quite a weak one.
Right.
But it's still nice.
all crazy.
It's an insanely sensitive detector or instrument. So yeah, we have one of these. There's a few of these in different locations. So here's a picture of Hanford at the top left, Livingston in Louisiana, and Virgo in Italy. So we have multiple of these detectors because you sort of need that if you want to sort of claim a detection, or it helps a lot to claim a detection. But we don't just have those three, there are more. This is an old slide. So Virgo is not under construction, or it's constructed. And so is Cagra. And Lagunda is under construction. So this is a bit out of date. But we have a whole network of gravitational detectors around the world now. And yeah, this can help with both sort of validating that you've seen a detection. So if you see it in one detector, you should see it in another one shortly afterwards. If it's a short duration signal. And it also helps with sky localization. So if you see it in two different places, you can sort of narrow down where that signal came from. Because these detectors are not, directional at all. There's a little bit of directionality, but they're mostly just sensitive to all regions around. So what have we seen so far? So the first detection was back in 2015. So that was about 7 years ago now. And we've had 3 separate observing runs, which last around a year since then. And we're seeing around 100 detections in total. So these are all from compact binary systems. So that's either a mixture of black holes and neutron stars spiraling and merging. And this has allowed us to start to do more sort of actual research and actual physics with these observations. So there's things like measuring the Hubble constant, which people here will know about, as well as learning about populations of black holes and where they form or how they form and where they come from. So we're building up a huge number of detectors now. These are quite commonplace, and certainly moving into the next observing run, which should be next year, we should be seeing even more of those. So we should be building up a massive catalog of these types of signals. But compact binary coalescences aren't the only type of signal which we expect to observe. It's the only one we have, and we generally split these up into these 4 categories of search, of the types of source even. So compact binary coalescence are short duration signals, which are very well modeled. So we have a description.
Did you say you don't really separate them into these 4, or you generally separate them?
We generally do.
Generally do.
So these are sort of 4 categories which we have, which are based on the sort of algorithms we use to search the techniques we use. And this is mostly based on how much we know about the waveform beforehand and the length of the signal. So a combination of those 2 things. So compact binary coalescence, the short duration from less than a second up to tens of seconds, depending on the masses of the objects. And they're well-defined waveforms, so we just sort of compare that with the data. We'll detect those. Another kind is continuous waves. So I'll talk a bit more about this later, because that's the more focus of this talk. But we expect these from things like neutron stars, so isolated neutron stars, which have some asymmetry in their mass distribution around their rotation axis, and that can emit gravitational waves. But these obviously, the neutron stars just keep spinning for a long time. So these are long duration signals, which last longer than your observing run, but are much weaker. Again, these are very well modeled signals, so we can write down the waveform for this model as well. But they're just longer duration. We can then look at bursts as well. So bursts are short duration signals, which you expect to come from something like a supernova. Or you can have a close encounter of black holes. It could be like sort of catapulted around it, like a short burst of gravitational waves. But these are not very well modeled. So these are short duration, but not well modeled signals. And so you generally look for sort of high power events, and you correlate those between different detectors. And that's how you generally search for those. Finally, there's stochastic signals, which are persistent system signals. So they're long duration. We don't have a waveform for them either. And these will generally come from things like if you have a set of supermassive black holes, for example, and there's lots of those signals coming at you, but you can't resolve any of those individually. They make up sort of background of gravitational waves. And so you can look in sort of power spectrum and try and identify if you can see those. And there's also sort of the gravitational analogs of the CMB, which we should be able to observe at some point. So that's the general source categories that we have. But I'll talk mostly about continuous waves from neutron stars. So,
Joe, maybe an unfair question because I know it's not your area, but
yeah.
Why do you say the stochastic background is not well modelled? Because people.
Sorry, yeah. So, but what I mean by not well modelled is we don't have a waveform for it. So they have a model for the power spectrum. Like so there are models for it. We just don't have a clear description for waveform that has data.
So, but what would a stochastic background give? Wouldn't it just be like a constant? Or?
I think not necessarily, because I think it can be spread over a certain range of frequencies. You would expect a certain power spectrum which you could identify above the noise level.
So there is some modulating signal.
Yeah, and I think you can also correlate that between multiple detectors as well. And if you see the same sort of signal in each of those, then I think I'm not an expert on that, so that's my memory of how that works. So neutron stars. So this is what I've done a fair bit of work on in the past is searching, developing techniques to search for these. I've seen a lot of these already. I've seen about the last time I looked was about 3,000 in our galaxy by EM emissions. So you see this with radio or X-ray or others, so we see these mostly as pulsars, right? So you see emission out of the pole of the star, and that sweeps past you, and you can observe these. There may be many more of these sources, rapidly rotating neutron stars in the galaxy, which we can't observe with EM, either because the beam is sweeping past the Earth or because it's not emitting. And so if we can observe these gravitational waves, we can start to build up more information on the population of these within the galaxy and learn more about these. And as well as that, we can start to learn more about the structure of the neutron star itself and the equation of state of that. And so this is a goal not only with isolated neutron stars, which I'm talking about, but also binary neutron stars as well. So you can learn a lot about the equation of state and how it's sort of squish by observing this, because it has an effect on the waveform of the signal. Okay, so how can neutron stars generate gravitational waves? There's a few ideas of different mechanisms that cause this. Basically, what you need is some mass asymmetry around the rotation axis, because you need to have quadrupole gravitational waves. And so the key idea, or the main idea, and the main thing which we search for are what are called neutron star mountains. So a neutron star is pretty much spherical, but you can have sort of some small mountain on the surface of that, which as it rotates can emit gravitational waves. And there's a few ways that you can generate that. One is you can have a deformation in the actual crust of the star, and that can come from when the neutron star was formed, or potentially from a glitch or something like that. We can have really strong magnetic fields. I mean, a lot of neutron stars have strong magnetic fields anyway, and so this could potentially sustain some deformation in the crust of that star. And that's one potential mechanism of emission of gravitational waves, and that tends to emit at 1 times the rotational frequency or 2 times the rotational frequency of the star. And so that's the main thing we search for, but there are other ideas as well. So there's things called R modes, which I don't understand quite as well, because they're quite complicated, but basically you get, so your neutron star has a crust to it and then some neutron superfluid in the center of it, and you can get oscillations in that superfluid underneath. And those oscillations can sort of lead to gravitational wave emission, and that gravitational wave emission can also drive that mode more. So you end up with quite strong emission, potentially. Yeah. Finally, there's also accretion. So this is one which we search for quite a lot. So if you have a neutron star and it's in a binary system with some other companion star, it can accrete matter from that, and that can spin up the neutron star and also sort of create a hotspot on the surface, which again could create some sort of mountain or something like that. And that's another way to emit to emit gravitational waves. And we can search for these directly because we've observed some of these before in binary systems as pulsars. And you can sort of have some sort of estimate of how strong you expect a gravitational wave to be from those by how much matter is accreted. So sort of through, there's many other sort of ideas how neutron star and its own emit gravitational waves, but they're sort of the key ones we focus on and search for.
When you say mountain, you're talking like a centimeter or something.
Oh yeah, I should say mountain is an exaggerated word. I think they're constrained to be less than a millimeter. Or something.
Yeah.
So they're still quite spherical,
Right.
and it doesn't have to be sort of a physical mountain on the surface. It could just be a change in
Quadrupole,
density
right,
in some area of the star.
They're long-lived though.
They're long, yeah, they're long lived. I mean, these last for longer than observing runs, so we expect to observe them over multiple observing. Okay, so how do we search for these things? So a sort of a brief crash course on some data analysis for gravitational waves. We tend to observe some piece of data which we expect to have a signal which has some set parameters and noise from our detector or the environment around our detector. And what we want to do is extract that signal. So this works for sort of well-modeled signals like continuous waves or CBCs. We do something like this, where we can set a sort of a template bank. So we can generate a waveform for lots of different places in our parameter space. So you can imagine lots of different positions on the sky. We can place lots and lots of templates. And so this diagram here just shows a placement of some templates. I mean, these are meaningless dimensions, but you can imagine that's our ray of deck in the sky. And what you want to do is you want to place them sufficiently close enough that you don't miss any signals in between. And so here there's these sort of pretty circles going around this, but that's sort of representative of the area where you wouldn't miss a signal. You wouldn't lose too much SNR by using the wrong template. And so you want to have that overlap enough that you don't miss anything. So generally we'll create this template bank and then you compare that to your data, more or less. You can do a match filter for each of those for your signal. And then you can use the statistics which you get out at the end to claim the detection, to not claim the detection. That's the general idea, the very broad term. There's some issues with this with CW analysis, but I'll talk about these in a moment. First, I'll talk about the model we use for continuous gravitational wave. So it's pretty simple. It's just a pretty constantly rotating neutron star, which in theory should be emitting gravitational waves, so that rotation frequency should slow down over time. So it's in its simplest term, it's just a sinusoid with a decreasing frequency. And for these are long duration, like that, as I've said, these last for years. It should last for multiple observations. There are some searches which run for short durations where these can just turn on briefly and turn off. That could happen after, say, the glitch of a neutron star. It can suddenly spin up, emit some gravitational waves, and then spin down again, and you can't see them anymore. But they're very weak signals, right? So this is a sort of an estimate of some of the strain. So we estimate this based on the rotation frequency. It's the F, it's the square and rotation frequency. It's quite strongly dependent on that. The distance at the bottom, and then this epsilon is sort of the ellipticity. So that's sort of how we measure the mountain of your star, if you like, how much it's squished. Because that mountain can often just be like a rugby ball shape of your star rather than an actual mountain on one side. But if we put in some values which you might expect, so the source at kiloparsec at 100 hertz, and plug in some other values for ellipticity and the movement of inertia around the z-axis, and you get a strain of about 10 to the minus 26, which is incredibly small. If you think about the gravitational wave that was first detected, had a strain of about 10 to the minus 21, is about 5 orders of magnitude weaker than that. They're very weak and so hard to spot, so we have to really dig down into the noise of the detector to try and identify these. Yeah, so that's one of the issues with these. Another one being the signal is not quite as simple as just searching over lots of different frequencies or frequency derivatives with a spin down. But you also have a Doppler effect, right? So as the Earth goes around the sun and the Earth rotates, your detectors are on that, your signal gets frequency modulated. So the top here you can see sort of a spin down over time, and then these yearly oscillations as their frequency changes. And then at the bottom here you can see daily oscillations as well. So you just have Doppler modulations to the signal, and this is actually quite inconvenient because of what I mentioned earlier about template placement. And this makes it really hard because it's sort of like having a telescope with the aperture of the radius of the Earth, or Earth's orbit. And so you have really fine resolution on the sky, so you need to place a lot of templates. I'll come back to that in a second.
You don't have the Doppler shift at the other end as well, because presumably the neutron star is in orbit around something.
So if it's in a binary system,
Yeah.
there is extra parameters to this, and you also have to include that. But a lot of the searches we run are just for isolated neutron stars. So there's different kinds of searches that are for each of these. But yes, you're right, you would have that. Yeah, so as well as the Doppler modulation, you have amplitude modulation as well, because these detectors are not equally sensitive to every direction. So sort of in the plane of your detector arms, so if it's coming from above the detector even, that's where you're most sensitive. If it's coming edge on, you sometimes won't see anything at all. And so these two plots show at the top here, show the sensitivity to different directions of the gravitational wave, or where it's come from, relative to the two arms of your interferometer. And at the bottom here is just a time frequency spectrogram of some simulated gravitational continuous wave data. So this is over a few days. You'll see it changes frequency with a frequency modulation and then the amplitude modulation as well. Switches on and off.
I'm sorry, what's the difference between the two at the top?
Sorry, that's two polarizations. So there's two polarizations you get: gravitational wave, a plus and a cross. And they're rotated by like 45 degrees from each other. And that's just sensitivity to each of those. So yeah, so the signal gets a little bit more complicated, adding these extra modulations to it. But in theory, we just have a model of our gravitational wave. So we have our amplitude, which is a function of the frequency and distance, as I mentioned before. You have a frequency of rotation, and you have an inclination and polarization. So these two parameters are basically related to the orientation of the source relative to you. So if your neutron star is tilted towards you, that's the inclination. So if you rotate that round, that's related to the polarization. And you also have a sky position of where you observe this. And that's basically all the parameters there are for a CW signal. So it's relatively simple, and we can just write this down and get a waveform out of this quite easily. And then you can do something like your match filter. This is just basically what a match filter is, and you set up some statistic based on that, some detection statistic, I should say. Now, this is what we do in some cases, but there's three different kinds of search categories for us when searching for neutron stars. There's what we call targeted, directed, and all sky. So we have information on a lot of neutron stars, where we've observed a lot of them electromagnetic, and so we can use that information to try and target our search towards what we want to see. So these targeted searches use the frequency derivative, and sky position of a source, and we use that information to generate a template, which we can then just compare straight to the data. And you can allow for some changes in the frequency and things like that if you want to. And these are the most sensitive searches that we have. You search over a full year's worth of data. This is a lot of data. I mean, we sample at 16 kilohertz, we downsample to 4 kilohertz and it's about a year. So it's a huge amount of data you have to run this over. But these are the most sensitive searches. Aren't actually particularly computationally costly, only because we have to generate basically one template to search for. When you don't know the frequency and the derivative of a source, you just know where it is, it starts to become a lot harder, because then you start having to create lots of templates for every different frequency and every different frequency derivative. And the spacing you have to place those is for frequency is 1 over the length of your observation, and for frequency derivative is 1 over the length of your observation squared. That's the spacing. So you end up having to place loads and loads of templates for this, and it starts to become very difficult. And then if you move to all sky searches, it becomes even more difficult, because you have to have templates over the sky and all frequency derivative. So you end up with almost an impossible task. I say almost, it is an impossible task to run a match filter for all of those templates. So here's an example of a tiny section of data you might have, where you have a pretty strong signal in this, which is the red curve, and then some noise on top of that. And that red curve is sort of your match filter you just compare to your data. Now, if we come back to the placement of these templates, if you wanted to do that across the whole sky for a year's worth of observation, you'd need about 10 to the 14 templates over the sky. And to run a match filter for a year for 10 to the 14 templates is not possible with computer power that we have in the world at all. So it's quite a challenge. And that's not even accounting for the templates you then have to place in frequency and frequency derivative as well. It's cover your entire parameters. So what do we do instead? So instead, what we can do is break that data up into lots of little chunks. So if you make your length of observation that you create a filter for much shorter, you don't need as many templates. So you can actually run your search for a short segment, and you can do that through the segments after that. So here we've broken up into 4 segments, done a sort of match filter for each of these, where you coherently search in each of those chunks. This has a massive improvement in speed, because your observation time is much shorter, but you lose a bit of sensitivity because you're breaking them up, and you're no longer coherently searching over your entire observation. Once you've done this for lots of different separate parts, you can then combine your data together at the end in some way to get your final detection statistic.
May I ask a question?
Yes, go ahead.
did you have a way of choosing the size of those chunks, or did you just kind of figure we'll make it this?
So there's a few different ways. I mean, I'll talk about them in a second. I'll go to the next slide just so you can see. But the default we sort of use for these little sky searches, which most of what I've worked with, is half an hour long, because that way you don't need to worry about the frequency changing within half an hour. So you can just do a Fourier transform. So you don't need to actually generate a filter or create a filter. You can just do a Fourier transform, and it should remain roughly within a single frequency bit most of the time. But there are searches which use longer ones. Basically, you want to use as long as you can the computing power allows. So there are searches which do this in steps. So they start with really short observing times, and then if they find an interesting candidate, they'll increase that around where that signal is. You do it in a sort of a ladder up until the full observing run. They're quite computationally costly searches. Still, it's not actually done by LIGO anymore. That's an external group that does that now. But yeah, for most of our sky searches, we just use half an hour on Fourier transforms because it's just quick and it's easy. But it's how we combine those results. And there's a few different ways that we combine those sets of Fourier transforms of our data. So once you have that, you can imagine a signal which has a Doppler modulation sort of changes. So this goes down in frequency and up. So those green squares are sort of where the signal is, and you can demodulate your set of SMTs based on a particular sky position. And if you were to choose the correct sky position and shift all your frequencies around, you should be able to line up your actual signal. And then the simplest way to deal with this is just take the sum of the Fourier transform power along a straight line. And for that frequency, that's your statistic, basically. So that's sort of quite a simple approach to this, and there's a few other more complicated approaches. The idea being, if you demodulate it for the right signal, you should have a higher statistic. If you demodulate it for all the wrong sky positions, you'll have some other background distribution. So down here you can see sort of grey curve is what you would get for demodulating for lots of incorrect sky positions or just for noise. And then as you demodulate for correct sky positions, you get higher distribution of statistics.
Sorry, this is accounting for Doppler.
This is just accounting for Doppler, yes.
Yeah, okay.
So there's a few different ways you can do this. There's a few different searches. One demodulates for the Doppler shifts, and then searches over frequency in f dot. And another one demodulates frequency in f dot and then searches over the sky. I say. So there's a few different ways you can approach this. But the way which I'm going to talk about mostly today is what we ended up doing in Glasgow, which is basically to throw out a lot of what we know about neutron stars and what I've just been talking about and try something completely different. So we developed something called SOAP, which stands for snake on a plane, because we search for snake-like patterns in the frequency plane. Very pleased with the name. The reason we sort of developed this is because searches take a long time. So these all sky searches, even after doing half an hour SMTs, short Fourier transforms, so short Fourier transforms, they're still very slow, so they can take weeks to months to run after the end of your observation. And that's quite slow still. So we wanted to speed that up and have something which can run more rapidly. The other reason is we also wanted to search for stuff or signals which doesn't follow the standard frequency evolution. So I would search things, long duration signals, which we don't really know where they come from, potentially, to try and find something new. But this can also exist in neutron stars as well. I can have a glitch halfway through, and that'll throw off your template, whereas we wanted the technique which can just smoothly transition between those two. And with some neutron stars as well, you can have sort of random spin wandering. So this should be able to account for that by allowing some different frequency evolution from what we expect. So as well, it's a really simple search. At the core of it, the idea is really simple. So you can imagine a spectrogram like this. So a time frequency spectrogram for about 400 days of LIGO data, or simulated LIGO data, over about a 0.1 Hertz band. And you can imagine just a track running through that. So track through the time frequency plane. Well, we put some constraints on this track. You say it can only jump by a single frequency bit at each time step. Because we don't really expect an astrophysical signal to jump too far. They jump by 10 frequency bits at each time step. So you put that constraint on, and then you can draw any number of tracks through that. And if you were to look at every possible track, starting at this side and then at this side, and you get every track running through that, you can build up some distribution of what that looks like. So at the bottom here, you see this green histogram is a subset of all the possible tracks. We can't actually compute all the possible tracks because that's another unimaginably large number. But you can imagine if there's a signal, so where this red line is at the bottom, I object is just a fixed frequency signal in there. And where that is, you end up with a statistic which is much larger. And this statistic, sorry, I should say, is basically The simplest form is just the sum of the Fourier transform power along the track which is found. And so, yeah, if there's a signal present, then you would imagine the track that follows that signal should give you a much larger value. And so our plan was to use this as a detection statistic. So if you could find the track which gives you the maximum sum of power, that's the most likely to be associated with the signal.
I get the tracks concept. I didn't quite understand the signal that is leading the thing at the bottom to be optimal. Can you explain that?
Sorry, yeah. So if you looked at every possible track through here, you build up this distribution, and one of those tracks would follow the same frequency evolution as your signal. And if you took the sum of the power along that track, it should give you a much higher value than if you did that for any other random noise track.
I see. So the peak of this distribution is when this statistic is when you've hit the correct signal.
So the peak of this is sort of the average sum of power you'd expect from any random track for your data. And if one followed your signal, you'd expect it to gain a little bit more power at each step.
Yeah.
And so that's sum up to a much larger value. So you'd have something like over here.
Okay,
So you
fine.
have much
Sorry, so
larger
not the
value.
peak, that line.
So yeah, so the peak is your background distribution. Basically. And this is
Okay.
your-
Okay, got it.
Does that background distribution change if the jump probability changes between frequencies? Does that question make sense?
Yes, and yes. Basically, yeah. So we spent a lot of time trying to decide how we decide what probability of jumping up a frequency bin or staying the same or jumping down. And we ended up setting into equal probabilities seems to work as well as others in a lot of cases.
Like 1/3 each.
So was that?
1/3 each.
Yeah, 1/3 each, basically. And that's generally what we run for all of our searches. Because the doctrine modulation goes up and down to expect a similar probability for both. In fact, it's more likely to go straight than anything else, but I don't seem to have much of an impact on the results of this in the end.
Interesting.
But the key thing about this algorithm is that we don't have to search over every possible track because we have about 22,000 half-an-hour SLTs and about 180 frequency bins in a 0.1 hertz band. We tend to search over quite narrow bands in frequency. And if you want to search over, identify every possible track, like a brute force sort of way, it'd be 3 to the power n times n, where n is the number of time bins and n is the frequency bins. And the 3 is because you have 3 jumps each step. And that's not possible to do. I don't really know what that number is, it's very large. But we use something called a Viterbi algorithm, which sort of optimizes at each step. And I can find the track which gives you the maximum sum of power. And it does this really efficiently. It does it 3 times n times n. I won't explain exactly how the algorithm works, but you can sort of just trust me and believe me that it does find the optimal track.
That's quite cool. So they peter out like halfway, lots of them, when they aren't at.
Yeah.
Right.
So this bottom
Yeah,
one is sort of is the statistic you get at each stage of the search. So sort of like related to the probability that a signal is present, and you get these sort of cones coming out, which are from each point, the track running off. So this is quite useful. So it returns this sort of probability map, if you like, of where the signal might be, as well as a track and some other statistic. So there's 3 main quantities that we return from this search. And this is just for a single detector as well. We don't just do it for a single detector, we have multiple detectors. So we can combine these with 2 or 3 detectors as well. And yeah, so generally how we run this search is we split up into 0.1 hertz band for about 20 to about 500. Oh no, we did it to 2000 hertz now. Split up into 0.1 hertz bands, then run this search. And it's incredibly fast, certainly compared to other searches that we have. So rather than taking these weeks or months, this takes maybe a few hours, something like that, where 90% of the time is taken up just loading in a bit of data. And you have to load in the next bit of data. So it's the I/O which is really the big problem here. So there wasn't much point in trying to speed this up anymore, basically. That's the point we got to. Now, it's not a perfect algorithm, it's quicker, but there's many problems associated with it. We're searching over a much bigger parameter space, so we have much more problems trying to identify candidates in our data. So one of the problems, this doesn't just apply to our search, but also all searches, we have massive problems with instrumental lines. So these are generally long duration spectral artifacts in our data. So there's a few in here I'll point out what they are. So this is a sort of a power spectrum or amplitude spectrum of the LIGO data. And there are some which we know about in here, some of these narrow band peaks. So there's violin nodes, which are the suspensions that hold up the mirrors at either end. They have some fundamental frequency, and you tune those to be about 500 hertz and to be as narrow as possible to keep them out of the way. So those power lines, which is the 60 hertz, which is the grid frequency in the US, and calibration lines which are deliberately injected into there to calibrate your detector. So these are all quite easy to deal with. You just cut those out and don't search there because you won't find anything. But then, as you can see from this, there's loads and loads of other peaks within that. And they can come from various different things. Really, really hard to identify. There's quite a few people who spend a lot of time trying to figure out where these come from and to mitigate them. One of them is blinking LEDs. So this was one which was found, which is a server rack at Ligate, which had a blinking LED, and it shared a power source with some other instrument and was drawing just enough power to couple into the detector. And so we end up with a comb of lines of different harmonics. But that one was found, so just unplugged it, plugged it in someone else, solved that problem. But there's many of these. I put in the pecking ravens, which isn't so much a long duration, these are more short duration signals, but basically there's some tubes going into the side of the detector, which had some frozen ice in it, and some ravens land on there and pecked on these, and you see these in the detector. It's weird features, which took a while to find, and then someone went up with a hammer and hit it and produced the same noise. So they now have anti-raven measures.
Did they have to go and clean out the pigeons from one of the early CMB experiments?
It's always
But these are a huge problem, right? Because these long duration, certainly the long duration narrowband ones, look almost identical to a continuous wave signal. Certainly, if the continuous wave signal is sort of directly above sort of the plane of the ecliptic, basically, because they won't have much Doppler effect. So there'll be flat lines, so you won't be able to distinguish them from an instrumental one. Not easily, anyway. There are some methods you can use, but when you're trying to search over the entire frequency space with sort of a broad parameter space as well, it becomes very hard to separate these two to make it tabulate all of your data. So how do we deal with this? Well, there's a few statistics we developed, because if you have two detectors and it's loud in one detector and not the other, you can sort of penalize that. But that's only one of the many different kinds of line which exist. So we turn to machine learning, because that's what everyone turns to when you're trying to classify two things. It's relatively easy, and we have access to a lot of data as well. So we basically this is quite a few years ago now, I'll probably update this with better now, but we basically fed in the outputs of our search along with the actual time frequency spectrograms into some convolutional neural networks, and just got it to predict a class of signal and a class of noise. So it's a relatively simple approach, but it's quite effective. So if you look at this plot here, this is sort of a plot of sensitivity, right? So the efficiency is the fraction of signals that we detect given the false alarm rate. So here it'd be a 1% false alarm rate. And at 100 SNR on this blue curve here, which is our original search, we detect about 95% of signals. And when we just throw it through a neural network, we trained this beforehand, we get sensitivity improvement and end up with about 70 SNR. So it's a substantial improvement, but this mostly comes down to rejecting spectrograms and outputs that look like instrumental artifacts. So it's quite useful in that sense of just filtering the output data we have. Because before that, it was basically just me looking and clicking through many plots and rejecting them. So I was sort of a machine in the past, trying to replace myself with this. And so that worked quite well. So it's a lot more sensitive in this case. That was stage one. So once we have this, say we were to have a candidate which we thought was interesting and wanted to follow up on that with maybe another search or just more closely, what we really want is an estimate of the parameters of that source, i.e. where it is on the sky, what frequency it's at, and the frequency derivative, because all we have at the moment is we just say it's in this band and there's a track associated. What we wanted to do is use those tracks to have some estimate of those parameters. And we could do some point estimates or something like that, but we wanted to go down the Bayesian method because that's generally what we do. And so we want a prediction of the parameters given the data, and our data is these frequency tracks. Now this is quite difficult. We found out quite early on, tried a few approaches, but to do like a traditional method of sampling like MTMC or method sampling, something like that, you need a description of the likelihood function. So you need a description of the noise of your data. And this is an example of the sort of noise we have. So a high SNR is very closely around the ejector signal, and a low SNR is sort of randomly wanders through the band. So each of these black lines are the same signal, but a different noise realization in your spectrogram. So it's quite complicated. And we tried for quite a while to write down a likelihood function for it, but didn't have much luck. So what we decided to do instead is just skip around that and use a method where you don't have to write the likelihood down. So this comes back again to machine learning, because everything does. So we use a method called a conditional variation autoencoder. I'm not going to explain the details of that, but just take it as a method which you can use to do Bayesian parameter estimation. So you can get Bayesian posteriors without having a likelihood definition. What you do is you show it lots and lots of examples of real data. So you're showing it lots of examples of your likelihood or samples from that, in a sense, and signal samples from your prior as well, and that sort of it learns that distribution for you. So this is used, and I'm currently still developing it for CDC parameter estimation. So we want this to give fast alerts on sky position or compact binary code distances as well. But we sort of stole this technique and used it for our search as well. So this is an example of a test case we did with sort of a Doppler curve, but with Gaussian noise added to it. So we could compare directly to a traditional sampler, and we just demonstrated that it works very well. And it closely matches the posteriors that you would get from a traditional method when using Gaussian noise. But that's not the problem we really wanted to solve. What we wanted to solve was our awkward tracks, which wander around and sometimes find the signal and sometimes wander off and find another bit of noise. And we eventually demonstrated this works quite. This is just one example. I've only got one example to show you, but again, just trust me that it did work on lots of others as well. But it sort of predicts where the signal is closely related to the track and where it wanders off. So it sort of estimate that for you, as while also estimating the set parameters. So these are longitude and latitude, as in sky position, frequency derivative. So it can generate these posteriors for you as well, which is really useful, because then we can take this and give it onto another search and say, okay, you can do like a templated match filter, this small region of the sky where it's actually possible for you to do that. So that was the general idea of this whole search. And so we run this in the third observing run, which is a few years ago now. And this is a sensitivity plot, which isn't necessarily a fair comparison. We're obviously the worst ones here, but we search a really broad parameter space and the signals we don't expect as well. So we never expect it to be as sensitive as everyone else. But there is 4 search pipelines. That's a big one here, sort of a baseline, which are running over 3, and they're running no detections, which is a big surprise. But we're looking forward to 04, where we're going to get more sensitive again, and there's a potential that we might see a signal there as well. But we're going to run this pipeline again and hopefully it will identify some of these neutron star signals. I think that's pretty much it for me. I'll leave a summary slide up there. But yeah, that's it.
All right.